Hello again, everybody. We're going to continue our discussion on derivatives. We talked a lot in the last lectures about how to find some of these derivatives. Now we want to take a step back and we want to remind ourselves why. Why do we care? And this, is a good question to ask. What is so special about derivatives? What is going to allow, or what do derivatives allow us to be able to do that we weren't able to do before? So I want to connect it back to an older concept, which was we had this concept of the average rate of change, also known as AROC, which was a change in the y divided by a change in the x coordinates. Now, if we redefine delta x, and remember, delta means change. Now, we've done a lot of work where h was our change, but it's a little more formal to call it delta x, change in x. We can write the AROC like this, the average rate of change. How do we jump from an average rate of change to an instantaneous rate of change? Well, IROC is the limit of AROC. We just take AROC and we put it in a limit, specifically the limit as delta x goes to 0. Okay, so here's the most important thing. If f of x measures a quantity, f prime of x measures the IROC of that quantity. Okay, so reminder, dy over dx is the limit as delta x goes to 0 of delta y over delta x. Okay? The connection being, this is IROC, a derivative. This is AROC. Specifically, what's inside here. Okay. As an example, let's say you have a function, let's say f of x is going to measure pounds of dog food, and let's say x measures days. And let's say we're a factory that makes dog food. So f of 5 is the amount of dog food produced on day 5. Whereas f prime of 5 is the change in dog food production on day 5. So to kind of connect it to some real values, let's say f of 5 is 10,000. But f prime of 5 is 250. It's going to be 250 pounds per day. We increased our creation of dog food by 250 pounds per day on that day. Okay? So, now, technically you can measure anything, but it's really, really common, as we've seen, to measure position, velocity, and acceleration. Okay? Now, real quick note, I want to point out, velocity can be, let me rewrite this, velocity can be positive or negative, depending on if you are going what we call a positive distance, and that means our distance is increasing. So you might say like, oh, your 0 is home, right? So when I drive to work, my velocity is positive because I'm increasing the distance from home. Versus when I drive home, my velocity is negative. I'm still traveling, 60 miles an hour, but now it's negative 60 miles an hour because I'm decreasing the distance from my reference point, which is my home. Okay? So, and we can always connect position, velocity, and acceleration through this derivative. Velocity is the derivative of position. Acceleration is the derivative of velocity, is the second derivative of position, acceleration. Now, here is the connection. If my position is increasing, and what I mean by that, if the position distance is increasing, my velocity must be greater than 0. Likewise, skipping down to the third one, if my position is decreasing, if I'm getting closer to a reference point, my velocity is less than 0. And this is an important concept that we will explore later on near chapter 4. If my position is not changing, if I'm not getting any closer or further away from my reference point, my velocity is 0. That is always, always true. And then also, if I replaced position with velocity, I could replace velocity with acceleration if I wanted to. And all of these statements are true. Okay? So, knowing the sign of your velocity or your acceleration tells you something about the previous example. If you tell me something about your velocity, I can tell you something about your position. If you tell me something about your acceleration, I can also tell you something about your velocity. Okay. I want to do a couple examples. One of the examples I want to do is fairly involved, so I'm going to go ahead and shout it out. This is question number... Looks like question number 8. I'm just going to read it. I'm not going to write it out. C of x represents the cost of producing X items. So we're just a factory that produces items. And C of X tells us what's the cost of producing that, where little p of X is the sale price per item if X items are sold. Okay? So, this is little p. Big P, which I'm going to try and change, is our profit. And it's defined as X times my cost function. Oh, apologies. X times my little p function minus my cost function. So it's revenue minus cost. Now, why is it X times P of X? This is a price per item. So I have to multiply it by the number of items. So the real question is, if I want to find the profit function P of X, we're going to start with there, I need to fill in what these are. And here's what I am told. I am told that C of X, in my example, is negative 0.01x squared plus 120x plus 100. And I'm also told that little p of x is 300 minus 0.1x. Now, I'm also told a value a, but that's not super useful right now. But the first thing that I want to do is I want to point out that I can plug this right here. This is going to be x times 300 minus 0.1x. And I can plug in this here minus, now remember, I'm minusing the whole c of x, 0.01x squared plus 120x plus 100. Let's do some distributions. I'll distribute out the x. It's going to be 300x minus 0.1x squared. Don't forget, I'm also going to distribute out this negative sign. I'll get positive 0.01x squared minus 120x minus 100. And last but not least, I think I can gather some like term. So I have minus 0.1x plus 0.01x. I think that's going to be negative 0.99x squared. I also have 300x minus 120x. That's going to be plus 180x. And then finally, a minus 100. Apologies for the typo. I checked it on my calculator. I incorrectly combined these. So that's my wake-up call. I'm sorry that I always wait for it to go wrong in a lesson, but I will start using my calculator from now on. So there's my function p of x. Now, we can also create what is called, if we go back up and we read, there is average profit, which is p of x over x, and there's also something called marginal profit, which is the derivative of p with respect to x. Keep in mind, that's a derivative. So, average profit, we're just going to divide by x. What I really am interested in, what is the marginal profit, which is just going to be the derivative of p with respect to x. So, let's find dp dx. You know what? Why am I rushing? Let's go ahead and find average profit first. It's going to be p of x, capital P of x divided by x. That's going to be negative 0.09x squared plus 180x minus 100 all over x. And let's find dp dx, which of course is our marginal profit. Now, I can find this by taking the derivative operator on p. I'm just going to plug in p, negative 0.09x squared plus 180x minus 100. Find that derivative. Whoops, wrong pen. This is a power rule and a sum difference rule. We'll bring down the 2. And trust me, I'm going to multiply it on my calculator. I got negative 0.18x to the 2 minus 1 plus 180x to the 1 minus 1 minus 100x, minus 0. Reminder, there's an understood x to the 0, and that's x to the 1. Simplifying this as best I can, negative 0.18x plus 180. That is what I would call dp over dx, or you could also call it p prime of x. These two things are the same. So you might be thinking, where does that a value that we talked about at the very beginning come into this whole thing? Well, now it wants us to evaluate the average profit and the marginal profit at these at this point. So a is 900. Let's go. Average profit is going to be negative 0.09 900 squared plus 180 times 900 minus 100, all divided by 900. That's marginal. Sorry, that's average profit. Now let's find marginal profit. That's going to be p prime of 900. It's going to be negative 0.18 times 900 plus 180. Now, if we plug these into our calculators, what we're going to find are, again, we get numerical values. But the important thing is we have to recognize what these values tell us about the world. What do they allow us to say about making these products or, doing some sort of operation? Again, not only am I interested in what these numerical values are, I'm also going to be always interested in, do I understand what I did when I took a derivative? Did I learn something? So what did I learn here? Well, if you plug this in, and I'll use some approximate symbols. You get about 98.89. And remember, this is an average profit. A profit, average profit per item. So it's $98.89 per item. But this is just what I might call a static. This is not talking about change. This is just a per cost basis. I'm selling these items, and for every item I sell, I know that I will make an extra $98.89. But what about this, which is 18? Now, because it's a derivative, this is dollars per item, but this is different. Because it's a derivative, it's a change. If I make about one more item. So, even though I can sell each of these items for $98.89 profit per item, if I make 900 of them, the question is, what happens when we go to 901? And the answer is, I no longer am able to sell or make a profit average because my costs change. It costs a different amount to make 901 objects than it does 900. Okay? So this is telling me my margins. If I were to increase, I should expect about $18 more profit per item if I were to increase from 900. That's the idea. That's my marginal profit. Okay? So, understanding derivatives, understanding that this is a fundamentally different idea is important. It's something that we're always going to be interested in. Okay? We're going to do another one that's hopefully a little more basic, which is most of them. So here's S of t is 21t minus 3t squared. Okay? So, first of all, we're going to find S prime of t, which is v of t, which is, again, 21 minus 6t, bringing down the 2. We'll also find a of t, which is v prime of t, which is s double prime of t, which in this case is just negative 6. So, here's the important thing to note. Question 1. When does the position not change? Well, if the position is not changing, that means v equals 0. That means 21 minus 6t equals 0. That means 21 equals 6t. That means t is 21 over 6. V of 21 over 6 equals 0. And that's an important observation to have. Question 2. When is velocity increasing? Well, velocity is increasing when the acceleration is greater than 0. But acceleration is negative 6, which is not greater than 0. So, when is velocity increasing? Never! Just because our acceleration is always negative, which means our velocity is always decreasing. Now, does that mean we're staying at a static speed? No. Again, the positive and negative of velocity and acceleration are mostly informing me about distance. There's a reference point. There's no such thing as 60 miles an hour for velocity. You're traveling towards or away from something. Okay? So, another question you might ask, determine the acceleration when velocity is 0. So, velocity equals 0, again, at 21 over 6. A of 21 over 6, well, that's just negative 6 just because it's a little boring. What if we had a different position function? Let's say something like S of t is 3t squared minus 4t cubed plus the square root of t. Well, v prime is going to be 6t minus 12t squared plus 1/2 t to the negative 1/2. And I could say that v prime of 1 is 6 times 1 minus 12 times 1 squared plus 1/2 times 1 to the power negative 1/2, which is 6 minus 12 plus 1/2, which I think is negative 6 plus 1/2, which should be negative 5.5. Or we'll say it's 21, sorry, we'll say it's 11 over 2. Now, another important thing that I want you to know is the position increasing or decreasing at t equals 11 over 2. Is the position increasing or decreasing? Well, if we want to know about the change in position, and anytime you think of the word change, I want you to think about the word derivative, which means the derivative of position, which is velocity of 11 over 2. Sorry, velocity of 11 over 2 is going to be 6 times 11 over 2 minus 12 times 11 over 2 squared plus 1/2 11 over 2 to the negative 1/2. Once again, we're going to plug that into our calculators. And the value that we get informs me something about the change. So I plug this into my calculator. And I got negative, let's say 329-ish. And the important is the position increasing or decreasing. Because this is negative, the position is decreasing at t equals 11 over 2. That's what you are allowed to say. So, hopefully this video helps you. Hopefully you're well on your way to start this new one. This is a slightly shorter homework section, but it's still a very conceptual definition that we need to master. Have a wonderful rest of your days, and I'll see you in the next lecture.